All right, I think we are ready for the last session of the day. Pleasure to welcome my colleague, Michela Tincani here. She will continue on the theme of sort of school choices, talk about using how to use subjective expectations data to estimate the educational choice models. We have 1.5 hours. Thank you.
All right, thank you so much, Dennis. How's it going? Are you tired? Because this is the last lecture of the day. What's your level of tiredness? Like 10? Raise your hand if it's 10. Okay, hopefully I'll make it sweet. And it's not going to be too, it's going to be fun, hopefully. I'll try my best. So as Dennis said, we'll continue with the theme of education that I think Arnaud was also talking about. And obviously the focus is how do you use subjective expectation data when you estimate structural models of education. I was told this was going to work. Okay, now it works. All right, so education choices are dynamic in nature. So for example, I need to decide whether I'm going to college. I need to compare earning loss today with potential future returns tomorrow. Or parents must choose a school for their child. They have to decide whether to pay for private school fees to go to a private school or to pay a location premium to go live near a good public school today. And then there's some uncertain return in the future for the child, achievement, future opportunities. College admissions, certain countries, college admission is very competitive. You need to decide, do I work hard today to prepare for the entrance exams instead of having fun? And that might increase my admission chances tomorrow. So there's these trade-offs where I have, to make a choice based on information about the future and in particular about causal returns to different choices that I may not be entirely informed about. So here I'm using the notation from Mansky's 2004 Measuring Expectations paper, and I try to use the same notation throughout. So imagine I'm a student, I need to make an education choice C, and I want to maximize my utility given a state of nature gamma star. You can think of gamma star as the future return to each of these choices. And then theta could be some preference parameters. So what is the problem here? The problem is that I do not observe gamma star. It's future. It's not only future, it's also causal, and we'll get to that in a second. So what do we do? Well, what we do normally is we're going to characterize or define a distribution over the unknown state of nature, and then we're going to maximize expected utility, right? This is what we're doing here. So suppose that we have data on choices, but we do not directly have data on these subjective expectations about, so this is a subjective distribution over the unknown state of nature. Suppose I don't have data directly on this. I just have data on choices. Well, it turns out that the parameters of these subjective beliefs about the future returns and the preference parameters are not separately identified if I do not make further assumptions. For example, if I see you decided to come to this course, did you come here because you think that this is going to help you produce a better job market paper, which then is going to lead to a better job, and so there's going to be future returns, even though you really hate structural estimation, or you really love structural estimation, you don't care about the future returns? I don't know. All I know is that you came here. I don't know why. And so that's a fundamental identification problem that we have. And typically, for a long time, and until probably the 90s, the typical assumption to do was to specify a model for this distribution over the unknown state space. So a model for the data generating process. And then we assume that the beliefs that people have about the distribution are rational expectation, are rational. That means my subjective distribution is the same as the objective distribution. And that's, we can do that. And boom, now we can separately identify the two. And that's what we've been doing for a very long time. Is that a reasonable assumption, assuming that people have rational expectations? So here I have a quote from Mansky. I'm going to read it. I would particularly stress that decision makers and empirical economists alike must contend with the logical unobservability of counterfactual outcomes. So let me stop here for a second. It's not only that these returns in an education setting are typically future, it's something about the future that I don't observe, but it's also something causal. You know, I need to know what's the causal effect for me of choosing economics instead of choosing literature, instead of choosing medicine. That's a causal return. We are all economists. We know how hard it is to estimate the causal returns to education. Now imagine we are saying when we write these models that the agents know the causal, are able to infer the causal returns. So just think for a second about how much we're really imposing on decision makers. Much as economists attempt to infer the returns to schooling on schooling choices and outcomes, youth may attempt to learn through observation of the outcomes experienced by family, friends, and others who have made their own past schooling decisions. However, you cannot observe the outcomes that these people would have experienced had they made other decisions. The counterfactual, by definition, you never see it. So all you have is observational data as you're making your decision. The possibilities for inference and the implications for decision-making depend fundamentally on the assumptions that youth maintain about these counterfactual outcomes. There's actually a nice paper that just came out on Restad by one of my colleagues, Rani Spiegler, who is a behavioral game theorist, who's actually trying to study how people infer about causal effects. Given that what they have available to them is observational data. I actually collected data, I don't want to go ahead of myself, but I collected data on expected returns to college in Chile, and we actually found that the expected returns were very similar to the correlational return, about 200%, which is the difference between those in Chile who have a college degree, the difference in earnings, between those who do and those who don't. Obviously, that's not a causal return. But that's what we are assuming when, so it's a lot. When we assume rational expectations, we're imposing a lot on our agents. So one solution to this problem, if you're not willing to make that assumption, is to actually use subjective belief data. And there's at least two kinds of subjective belief data that I've seen used in this literature. One is the subjective expectations about the returns, such as the expected earnings from various educational choices. But also people use stated choices. So that is the probability of making a certain choice in the future. So researchers ask, what do you think is your probability of choosing medicine? And what is your probability of choosing economics? And they ask them before they make this decision. There's a nice survey here on the type of belief data that have been collected, especially in education. So what I want to talk about today is ways in which these data can be used in the estimation of models. And basically what I did, I went to the literature, I found papers that I thought had some very nice insights, and I'll summarize them for you. So you can use this kind of data to inform the model, the decision-making model. You can use this data to validate a model. So you have a model in mind, let's validate it using this additional data. If you have a panel of beliefs, you can model learning, which is what Arnaud, I heard the last minutes of Arnaud's talk, that's what he was mentioning. Also, you can explicitly use this data in the estimation of your model to separately identify gamma and beta, so you can think of this as the preferences and the beliefs. And then what you can do once you've done that, you can use your model to simulate results under rational expectations, which is a benchmark. And that then comparing what you see in the baseline of your model or in the data to the rational expectation benchmark can actually be quite informative and quite interesting. So what I'm going to do today, I'm going to give a brief overview of points 1, 2, and 3, and then I'll spend a little bit more time on point 4. I'll also try to give you some practical tips for point 4 based on my experience. So let's start with the first purpose, inform the model. And I don't know, you can correct me if I say anything wrong, because this is one of his papers, a very nice paper, JP 2020. There's a lot in the paper, but here I'm just going to summarize what I think are quite important insights on how you can use this data. So I use here an example with just two choices, 0 and 1. Throughout, I will just use this example, but the paper is more general than that. So what they do a nice survey where they elicit for each student the expected earnings, so these are the gammas, in each occupation. So we're assuming there's 2 occupations here. And then they also ask them their stated probability of choosing that occupation in the future. So once you've done that, so for each person, notice that you ask them, what do you think are your returns in occupation 0? What do you think are your returns going to be in occupation 1? So now I am really seeing the counterfactual, or what people think the counterfactual is. So I'm not assuming anything about how people build that, form that belief. I'm just taking it from the data. Because I asked this hypothetical question, these are causal returns, believed. Right? These are the beliefs that people have about the causal return of 1 versus 0. And then they also ask them their stated probability of choosing a C in the future. So as I've estimated the expected earnings in each of these 2 occupations, obviously I can estimate the return of choosing occupation 1 versus occupation 0. I just take the difference between the 2. That's beautiful. Now for each person, I know what their expected returns are. And what Arnaud and his co-authors were interested in was trying to understand how people make the occupation decision, and is that driven by expectation about future returns, and if so, to what extent. And so here, what I think is very nice, what they do is first they show this point and make this point in a descriptive way. So no structure, nothing, just use the data you smartly collected. What do? They estimate an average treatment effect. You can think of this as treatment effect where the treatment is choosing occupation 1 instead of occupation 0. So here is just the average of the returns from occupation 1 in the entire population of survey respondents. And then you can think of an average treatment on the treated, and they do this in 2 ways. One way is, well, what are the average expected returns among those who in the data are observed choosing that occupation, because they follow the people over time and they see also the true choice in future. You see how that is an average treatment on the treated. But obviously, let's exploit the stated probability. Here, you can reweigh these individual returns through the stated probability of choosing occupation 1 over occupation 0. Of choosing occupation 1. So you can see how the weight here is not 1 or 0, but it comes directly from the stated choice probability. But the concept in the end, it's the same thing. It's a measure of an average treatment on the treated. And the key insight is, well, if the average treatment on the treated, so the expected returns among those who either chose that occupation or are more likely, report that they're going to be more likely to choose that occupation, are larger than the average treatment effect in the entire population, well, this definitely suggests that there is some degree of sorting on that. So people sort on ex-ante expected gains. And they do find that. So they do find that ATT is greater than ATE. So you see how just descriptively, this is already informing a model. If you want to inform a model, it turns out these expected beliefs about expected returns actually carry information about how people make choices or want to make choices, because these are stated beliefs. If I remember correctly, you also show that the stated beliefs predict actual choices over the actual choices in future. Yes. What other thing they find? That 73% of the students did not place all mass on the highest return occupation. So there are people who say, I think this is the highest return occupation, but they're not saying I'm 100% likely to choose this occupation. So this suggests, on one hand, students positively sort on gains. On the other hand, it seems like something else also matters. And so this first descriptive analysis is quite interesting, And the conclusion from that is that probably an appropriate model here is a right model of occupational choice that is based both on expected earnings, but also other non-pecuniary factors. And so this is then what they do. They estimate such a model. Here I'm going to show here I'm just going to show some insights, a snapshot of the model. So what they do here, suppose you have only two choices, and you have a utility from choice 1 and a utility from choice 0. They assume type 1 extreme value shocks. So the choice probability, if you take the difference of the logs, that's the inversion that I'm sure you've seen. That's going to give you the difference in utilities. So notice that this is data. You can get this from the data, right? So that's going to be equal to the difference in utilities. What they do, they regress this difference in utilities, which remember is data, on what? On this, which is the difference in the log earnings, and on some characteristics, baseline characteristics of the student XI. The idea is that this alpha is going to be informative to calculate the elasticity of the choice to earnings, while this beta is going to tell us, well, the importance of non-pecuniary factors. It's going to capture the importance of non-pecuniary factors in the occupational choice. So what they do here when they estimate this regression, and again, there's way more in the paper, here they're going to assume that this error epsilon is orthogonal to the earning term conditional on the X. So this, for example, will be violated if beliefs and preferences correlated with each other. If beliefs and preferences that are not captured by the X correlated with each other, that would violate that assumption. So let's make that assumption for now, and let's see what we find. Well, what they find is that this alpha is positive, which is consistent with what we've seen earlier. That suggests there are sorting based on ex-ante gains. But beta is different from 0, so other factors matter as well. This is the elasticity that they estimate. A 10% increase, this should have been an up arrow, I'm sorry. A 10% increase in expected earnings leads to a 7.9% increase in the subjective probability of choosing that occupation. So that's the elasticity that they estimate. So a result from this paper is confirms positive sorting on perceived returns, but also there's a large share of people for whom non-pecuniary, I mean, there's a big importance of non-pecuniary factors as well. Again, what I want to point out here is how smartly collected data on subjective beliefs can help you inform a model. And then they actually also went ahead and estimated that model. So that's the first purpose of this kind of data, inform a model, understand how people make decisions. Yes?
This one can also be like an element of like a risk aversion that I guess you observe, you worry about you might not earn expected.
Yes, there could be. I can't remember what you assume or know about that, if you have linear utilities.
Because we were asking exactly that. So we, as Michela was alluding to, we do estimate a straight on all that simple like that, where we do have a CRA. We do have that. We do a regression, and it doesn't, it changed the magnitude a little bit, but the key message.
Thank you.
Just one thing I wanted to add. Then what is tricky is that we don't collect, we just collect the subjective mean, and so then we need variances for the, and so we basically assume that the variances are given by the exposed data. So it's a bit of a difficulty. Yeah,
I'm gonna mention a little bit about that. But that point is about what do you elicit about the distribution, right, of future earnings? Because you can elicit the mean, that's the easiest thing to elicit. But you can also elicit the entire distribution. People have done that by, well, Orazio has done it, by I don't know if Arnaud, you've done it more recently, apologies if you have, eliciting points on the cumulative distribution function. And obviously the variance around the mean, so you can think of individual level distribution of the subjective beliefs. The variance around the mean is a measure of uncertainty. We'll talk a little bit about that towards the end. Second purpose, model validation. Okay, so again, let's stick with this example of just two choices. So the random utility, this is the deterministic part of the payoff if you know the state of nature, like the return from that choice, future return from that choice. This is a shock, a preference shock. But I do not know the true return, but I have a subjective belief distribution about it. So then the probability of making this choice, it actually depends. It's obviously equal to the probability that the utility from option 1 is greater than the utility from option 2, which is driven both by the distribution of the shocks, but also by the subjective distribution of the future state of nature. So the choice probability, again, depends both on theta and beta. Now, suppose I have a model. I set up a model where I specify this Q. I don't have data on it, but I specify this Q. I can derive the choice probability. Here I assume type 1 extreme value. This is what the choice probability would look like. And again, I have fully specified this Q. For example, rational expectations, right? The expected choice probability depends both on the structural utility parameters and what we assumed about the belief distribution. Now, suppose that I have data on the probabilistic choices, on the stated choices. So this is how you can use that data. Well, what is a stated choice? Well, it's a probability that you will make a certain choice. But I just fully specified a structural model that gives me endogenously that probability. So suppose I can estimate this model without using at all these subjective stated choices, so the probabilistic choices. I go ahead, I estimate the model like in the old days, and then I say, okay, let's endogenously generate the probability of making a choice, and let's compare that to the stated choice. If they are the same, or statistically the same, well, that is actually a validation of my model, right? I found this in a very old paper from 1985 by Ken Wolpin and Gonol. Ken Wolpin was my advisor. And that's one of the earliest examples that I've seen in this. I put this paper in the folder, and I suggested you read it, especially the introduction, because it's very beautifully written and very simple. What they did in that paper was a little bit different from this. They have NLSY data on expected earnings, so the expected age of retirement. People are asked, when do you expect to retire? At what age? And they interpret that as the average expected retirement age. And then they follow people over time. So then they estimate a model, labor supply, a dynamic model, labor supply decision with the decision of retirement. And then without using the expected retirement age at all, and then they generate from the model the expected age of retirement, which you do by generating endogenously the expected probability of retiring at 60, the expected probability of retiring at 61, and you take a weighted average, and that gives you the expected age of retirement. And then they compare that to the stated age of retirement. So the one age of retirement that people reported in the sample. And what did they find? Well, they found that the two did not match up. So that actually did not validate the model. And so what do you do when that's the case? Well, here's what they did. They're like, well, this is the algorithm that they came up with. Check, let's not give up on the model yet. That's if you really believe in structural model, let's not give up on the model yet. Let's first check if expectations are better than the model at predicting actual future choices, because they have the actual future choice. Of course, they were. Expectations were. So at that point, you realize, okay, I need to give up on my model, my much cherished model. But what that means is that expectation data does contain information about choice determinants that is not captured in the model. For example, you assume rational expectations, but individuals have biased beliefs, for example. Now, this is a beautiful application of this context. Fast forward between 1985 2019, how many years is that? Many years, a few decades. And this is a very nice paper by Delavand and Zafar in the JP. And what do? They use exactly this concept of using stated choice to validate a model of university choice in Pakistan. In the papers, there's a lot more, so I recommend that you read it. But this is an insight that I found particularly nice. So this is a setting in which individuals need to decide which type of university to go to. There are religious schools, non-religious schools, international schools. in Pakistan. And they write a model in which monetary returns, non-pecuniary factors, and financial constraints all determine the choice of university that you want to go to. So then what do? They actually elicit stated choices at baseline. At baseline meaning, I ask you, what is your probability that you will go to a madrasa, which is the religious school? What is your probability that you will go to the American university? What is the probability you will go to this university? This just asks the question, what's the probability you go? That's interpreted as in whatever situation you are now, right? Whatever situation, in particular, whatever financial situation you are now, what's your probability of making each one of these choices? But then, and that's the beauty of when you go and collect your own data, they also asked counterfactual choices. So they ask, in a hypothetical scenario in which you had no financial constraint, what would be the probability that you would make this choice, that choice, that choice? So these are counterfactual on multiple levels, both because I ask about each choice, obviously you're gonna make only one, so all the others are counterfactual, but also because it's in a hypothetical scenario that never realized. It's when you don't have any financial constraint. So that's what they do. And then what do? Well, they estimate a life cycle model using the stated choices, that's because they don't see them long enough, under the baseline financial situation. So they use, instead of using actual outcomes, they use stated choices. So the outcomes, otherwise it's a quite standard discrete choice model. But then the nice thing is that they can then use this model that they've estimated to simulate a scenario in which people do not have any financial constraints. They simulate that counterfactual scenario, and then they predict choice probabilities in that counterfactual scenario. And these are the counterfactual choice probabilities that they match up with what they collected in the data, with the counterfactual subjective probabilities. And here they do find that they validate the model, also because this model already at baseline is already incorporating a lot of data on beliefs and expectations and on the actual financial constraints. So it's a model that already quite accurately captures whatever biases individuals have. So they don't impose rational expectation, but there you go, they validate the model this way. So they leave out this data, don't use it in estimation, and use it to estimate the model. So this is just another use for you that you might find interesting in future on how you can use this kind of data. Validate your model. Third, modeling learning. And this is something that Arnaud has just said, has just mentioned as well. So beliefs evolve over time. You can start with a prior about your own ability, for example, or about the returns to different educational choices, and then you revise them as you gain more information. So here I want to talk about two empirical examples that have thought carefully about belief updating. First, one example by a paper, Steinbrückner 2014, on the process of choosing a major. And what they did, you know that in the United States, when you enter college, you don't choose a major immediately, but you have time to declare it later on. And so what they do, they survey students repeatedly over time, 12 surveys per year. So it's very intense. In fact, the sample size is not huge, but I think it's less than 1,000 students, but very intense repeated observations on students' beliefs about their likelihood of graduating in a STEM or a non-STEM degree. And then the other example is an example with an information shock on earnings. So this is Wiswall and Zafar, where they provided undergraduate students with the true population earning distribution. And they collected data on stated choice probabilities. So the idea here is that we can exploit the panel of beliefs to see how beliefs evolve. And also explicitly to estimate our model and to separately estimate preferences from beliefs, relaxing some of the assumptions we've seen before, such as the assumption that the two are uncorrelated. So let's start again with a framework where, very simple, you know, you have a binary choice, you're making a decision, as usual, you need to integrate out also the beliefs. But now we have a T subscript for the belief. So the belief can update over time. You get a signal and you update the belief. So Steinbrückner and Steinbrückner do exactly that. They estimate a model where they have this belief updating, and what they do is, so here is belief about the likelihood of graduating. The insight from that model is to explicitly model the belief updating using the data, just exploiting the data that I have. I don't know exactly where this belief updating comes from, but I'm just gonna say that your posterior belief on the left is a function of your prior belief. Obviously, these are repeatedly collected over time. Your prior belief, and then whatever signal you get this year. And the signal in this case is going to be GPA. So you have your expected expected GPA or likelihood of dropping out are these two that you repeated over time. And then you have a noisy signal, which is the actual GPAs you get. So because they collected all of this data and they asked about the expected GPA in various majors, the insight of this paper is of trying to see how these beliefs evolve and how they evolve differently across majors, how important is the GPA in mathematics to update my belief about how well I will do in medicine, and all the cross examples you can think of. And what they find by doing this exercise is that it turns out there's something special about STEM majors. It turns out that only grades in STEM courses affect the beliefs about STEM performance in future. So the coefficient on the signal is 0 if that course was not in STEM. And so that means that they revise science graduation probabilities more slowly than in other courses, and this has then trickle-down effects. It takes you longer to drop out. It could potentially have worse effects down the line. And he can see this only because, I should say they, but it's Todd Steinbrückner wrote this paper with his father. His father, I'm not sure he actually, that's why it's Steinbrückner. I'm not sure his father is an academic economist, but he's a mathematician at Berea College. Okay, because this was at Berea College. So I don't know what so I said he collected the data, I should say they, but I don't really know what his father did. But it's because they have this very detailed panel of beliefs over different majors. It's in the end, it's quite simple what they do, but it's very powerful what they can do because they've collected this amazing data. I want to talk about Wiswol and Zafar because there's a link to Arnaud's paper here, because they do something quite similar but different. So here, Wiswol and Zafar, they have an experiment here in which they give people information, and then they see how people revise their information and how they revise their stated choices. Why is that important? What does that allow you to do? The goal of this lecture is just to give you ideas of how you can use this data and all the amazing things you can do. Again, here's a sketch of what they do. Again, assume 2 majors. Of course, the paper is more complicated than that. So this is student I's utility from major J. So it's going to depend on some covariates, baseline covariates. It's going to depend on your expected earnings. So this is the weight on the earnings. And here we have a time invariant taste shock for major J. Yeah? They assume type 1 extreme value as usual. Now, if you take the log odds of choosing major 1 versus major 0, I think I've got rid of the x's in here. Imagine there could also be x's in here. This is quite similar to what we've seen before in Arnaud's paper. But there's one difference, though. There's this term. They assume that this error term, which is a little bit ad hoc, you have to add it exposed, but they assume that this error term is orthogonal to everything, but this, which is your idiosyncratic preference for major 1 with respect to major 0, could actually correlate with the expected returns. So for example, if I like medicine more, I may also tend to believe that the returns to medicine are larger than someone who likes medicine less. Suppose that's the case. And that's what was ruled out in Arnaud's paper. He allowed for that based on axes only, but not in this case. So if you, this is data, as we saw before, right? This is a difference in the log stated choices, so that's data. We know it's a difference in utilities, so this is data. So if you run a regression of this on this, well, you're gonna get a biased estimate of this if this is correlated with that, right? So they wanna allow for a correlation between beliefs and preferences. Why can they allow for that? Why in the end are they able to estimate this theta E? Because they do an experiment. They do an experiment and they say, okay, I'm gonna collect people's stated choices of doing each, here it's major, it's not occupations, but it's majors. Then I'm gonna give them information about the actual, it's not really the returns. They give them information about the distribution of earnings in the population, and they're very careful about how individuals interpret that, how they infer from that their own expected returns. But for now, let's say they give them information about the true returns in terms of earnings, and then 5 minutes later, they measure the stated choices again, as well as their beliefs about the returns. 5 minutes later is the key. They argue, because we've asked them 5 minutes later, it's unlikely that their preferences for those majors changed. However, so that's an assumption they make. The assumption is preferences for those majors did not change because I've asked you 5 minutes ago. However, the expected returns changed, and they do see that because they measure expected returns before and after. So people do respond actually to the information, and they become a little bit more accurate. So once you do that, what can you do? Well, you can do basically a diff in diff, where this constant preference parameter cancels out, because I've assumed that's not affected by the information. So you can define, this is a difference in log odds post information and pre-information. It's actually gonna be, and again, this is stuff that you get from the data, because I've measured your stated probability before, I've measured your stated probability after for the different majors. So this is data. And this as a function of this difference in differences, which is, this is equal to that. Now, this error is now orthogonal because the thetas canceled out. So now, if I run this regression, this coefficient here is going to give me the true unbiased weight on earnings. And again, the goal here is to measure the elasticity. And here, surprise, surprise, they get a lower elasticity from the previous paper. So a 10% increase in beliefs about self-earnings in a major increases the subjective probability of choosing that major by between 3.6 and 6.2. Previously, which was occupational choice, but it was comparable, it was 7.6%. But here, because it's not the only reason, but one possible reason for this difference, aside from the different context, is that they allow for a correlation between beliefs and preferences. Yes.
After the paper, I just want to, just for, because of the paper for completeness. So there is one specification where we're doing exactly what you said, which is the 7.6, but then we use the fact that, we see the belief for different measures and different occupations. So we actually exactly have this kind of different.
Oh, okay.
Yeah. And so what we don't have is the experimental variation.
Yeah.
Experiment, as you know. So, but we do also find a decrease then. So that's consistent.
Okay, it's consistent. Okay.
Pre-specification.
I like that for the next iteration. But the idea is the same. So they also account for that. The idea is the same. If there is a correlation positive in this case between preferences and beliefs, you're going to overestimate the elasticity. Because you see that if earnings increase, you see people say they're more likely to then go into that occupation or choose that major, but it could be not an elasticity to the earnings, but it could be because actually those with higher expected earnings also like those majors more. And so that's why obviously it's a sign of that correlation, which determines if you over or underestimate the elasticity. If it's positive, you're gonna overestimate. So that's really nice. I'm totally adding it to the next iteration of the slides. Thanks for that. Great that you're here. I'm sorry for all the other authors who are not here. However, a common finding in these papers is that taste parameters are very important. Here they find it's actually one of the main drivers of major choices is you actually like studying that thing. It's not all about earnings. Last, and I have, yeah, halfway through, that's good. So last purpose. Suppose you have data on these subjective beliefs. You can use that to estimate your model, put that into your model, separately identify beliefs from preferences. You can relax rational expectation assumptions. And then once you've estimated your model, you can simulate what choices, outcomes, and utilities would have been if people had rational expectations. Obviously, the beauty of having estimated a structural model is that you can also simulate utilities. So you can also do welfare calculations. And so this allows you to, these simulations allow you to estimate the impact of belief errors with respect to a rational expectation scenario on choices and outcomes. You can also see how these belief errors interact with the effect of policies. You can calculate the welfare cost from belief biases. Basically, you simulate with your model choices and utilities and the rational expectations and in the Bayesian scenarios, and you see how the utilities change. Obviously, you make different choices when your beliefs are different. And also the interaction of belief errors with the welfare assessment of policies. And I'm going to talk about two papers that are within this, what I call purpose 4. Kapor-Nielsen and Zimmerman is the first one. So what they do, beautiful paper, it's a school choice model, and they have data on subjective admission likelihood to show, they demonstrate how the preference of belief errors affects the welfare assessment of the school allocation mechanism. Second example is my paper that I'm about to post the final version online, but it is on Dropbox, an incomplete version. In a week or two, it's going to be, it will have the conclusions. The version you have now doesn't have the conclusions. So what we do, we use a model of pre-college effort and college admissions with data on perceived returns to pre-college effort to measure how belief errors shape the incentive response to preferential admissions. I'm going to go a little bit more in detail, but let me start with Kapor, Nielsen, and Zimmerman. So the setting here is a school choice in New Haven, where parents participate in a Boston-style mechanism. What Boston-style means is that this is an allocation mechanism where parents submit rank order lists for various schools. The key here is that you get an admission boost if you put a school higher up in your ranking. Basically the implication of this is that truth-telling is not a dominant strategy anymore. So this can induce strategic behavior. And in particular, what is very relevant in that strategic behavior is what is your likelihood of admission. So if I know that my truly most preferred school, if I would have even zero likelihood, even with the extra boost I get, I still have very, very low likelihood of being admitted, I'm not gonna apply there. I'm not gonna put it in my rank order list. So really what matters to make this decision, this strategic decision, is the probability of admission, which in a mechanism where truth-telling is a dominant strategy, like deferred acceptance with an infinite number of choices, your likelihood of admission should not affect your choice. You should just report your truly most preferred in the true preference ordering. Okay, so what they do in this paper is they actually collect student subjective beliefs of admission in a given school, given an application ordering. Sorry, given a rank order list, so the preference orderings. And then what they do, they simulate the true rational expectation admission probability in each school, given the application that that candidate and everybody else has submitted to the system. Now, student I's decision is gonna solve this problem, and obviously the choice of application A affects your probability of admission. That's why the solution to this problem is not just to rank your most preferred, truthfully most preferred. So here there's a trade-off between the admission probability and the preference. So a strategic applicant may not want to rank a truly most preferred choice first if the chances of admission there are low. And so what they do, they exploit this data they have collected to try to find evidence of to show evidence of strategic behavior based on belief errors. So they show evidence that people appear to be strategic, but based on wrong information about the likelihood of admission. And sorry, that's the next slide. Before we get there, let me tell you that the beliefs are biased. So they construct the optimism as a difference between the subjective admission probability that they elicited from the survey and the rational expectation admission probability, which is simulated by running the algorithm. And they construct an optimism measure, which is a difference between the two. And this is a distribution of optimism among their survey respondents. On average, people are slightly optimistic, expecting almost 8 percentage point higher likelihood of admission than their true likelihood of admission. This is taking an average among all people and all schools, obviously. It's just a rough mean. Beliefs are off by 30 to 40 percentage points on average. So first, let me tell you, beliefs are wrong. They're not conform to rational expectations. And this is the evidence that strategic play based on biased beliefs. They asked students, what is your truly most preferred school? They asked families. Obviously, in a survey, they have no incentive to lie. Why would they lie? So this is from the survey. This doesn't come from the rank order list that they submitted, because we know that that one is not necessarily truth-telling. And then they plot that against their subjective belief of being admitted there. And you see that when people think they're more likely to be admitted there, they're also more likely to, they think, okay, it's probably a safe choice, and they're more likely to rank first their truly most preferred school. However, if you plot that, the fraction ranking the truly most preferred school first over the true subjective admission, the true admission probability, you see that this link breaks down. If anything, it even goes in the other direction, but it's definitely flatter. So they provide this as evidence that people are strategic, but based on the wrong information. And then they use this to estimate a model. To estimate a model under these biased beliefs, assuming people are strategic based on that information. And then they simulate two different school allocation mechanisms. The Boston mechanism, which is the current one, and deferred acceptance, meaning they assume that people just rank their most preferred, you know, they are truthful when they apply for schools. And then they calculate aggregate welfare. They just sum up all welfare. Obviously, aggregate welfare based on the actual allocations that people are given, based on the actual admission probabilities. Yes?
So how should one think about the fact that for acceptance, most students aren't actually truthful?
Yeah, they abstract away from that. So basically what they do is, let's assume people are truthful. That's what the algorithm really does. I think Chao Fu had a nice paper where she estimated the percentage of people who, no, I think she estimated the percentage of people who are truthful in when they shouldn't be. But so you're worried about deferred acceptance. Some people might try to be strategic because they don't understand.
Staying at the very same place. But if people have different rank order list formations, so some people skip impossible schools and some don't actually get different placements.
Mm-hmm. Yeah, they abstract. They abstract away from that. Yeah. So they basically do not even run an algorithm. They just assume that everybody ranks truthfully. That's what they do. So I should more precisely say they don't really run an alternative algorithm. They just make this assumption. But when you do that, you can then calculate under both mechanisms what's the actual allocation, who goes where, probabilistically, and then you can calculate aggregate welfare. And what they do, they now compare welfare under deferred acceptance and under Boston, but in two scenarios: under the observed subjective beliefs that they've estimated at baseline, and they find that deferred acceptance actually gives higher aggregate utility, higher welfare, student welfare, than Boston, 27% higher utility. However, under rational expectation, it would be the other way around. Actually, they would be quite similar. But Boston gets a little bit, gives a little bit higher utility, and that's the idea. That's because you can, you have a way to express how strongly you prefer a certain school by ranking it first, even if you don't have a super high likelihood of being admitted. So that leads to people who like that school more likely to be admitted. That's the mechanism behind. But the big insight from this paper is that if you ignore belief errors, you reverse the policy ranking in terms of welfare implications. They're the opposite. And I think this is a beautiful paper. I recommend that you read it because it's a beautiful way to combine subjective beliefs and models. And obviously, it's clear that when they went in the field to measure the beliefs, they knew what they wanted to do with it. So you already need to have in mind the model you want to use when you go in the field to collect your beliefs. Last, I'm going to talk about this paper. I'm going to spend a bit more time because I want to talk about a couple of tricks, practical tricks, or things that you need to be careful about. So this is my paper where we, with Enrico Miglino and Fabian Cosse, so we study preferential admissions to college for disadvantaged students. Why do these policies exist? To try and reduce gaps in socioeconomic status, college participation gaps in socioeconomic status. What these policies do, they change, for a certain group of people, they change the rules to be admitted to college. So obviously that means that they're going to change the mapping between effort and its rewards. Basically, they're going to have incentive effects even before college. They change your incentive. Suppose you don't need to do the entrance exam anymore, you're not going to study for the entrance exam anymore, for example. So it changes these incentives. And these are the incentives that we were interested in. And we were interested in understanding not only how they change the incentives, but how do students perceive that their incentives change? Because the two things could be different. Turns out we find that they are very different. And so that's what we're interested in. We're interested in understanding how do students understand these incentives, and in turn, how do these belief errors that we're gonna show we find, how do they shape not only the incentive effects, but then who ends up going to college and how well they end up doing once they go to college. So the longer term impacts of these policies. Not super long term, because we only look at persistence. We don't have graduation data yet. So let me tell you a little bit about this policy, which is called PASE. It's a program for support and effective access to higher education. It targets disadvantaged high schools in Chile. It started with the 69 most disadvantaged schools in the country, and then it expanded randomly, but they're still quite disadvantaged, those in those schools. And if you graduate in the top 15% of your cohort in your school, within school top 15%, you receive a guaranteed college admission. So that means you're competing just with other students who are equally disadvantaged to you. So that should make it easier for you. They can also take the national exam and apply via the regular selection process. They can still use the regular, they take the entrance exam, the higher the score, the more likely they are to be admitted. But on top of that, they have this additional channel available to them. Very disadvantaged schools, if you look at the academic preparedness based on grade 10 standardized test scores, these students are on average 1.5 students below, 1.5 standard deviations below regular college entrance. So that's a few years of knowledge below those who normally go to college. Socioeconomic status, the family income of these students is about a third the family income of those who normally go to college through the regular channel. So definitely disadvantaged population. It was very good at targeting who they wanted to target. So here we're gonna exploit the fact that in 2016, the policy was randomized across schools. So the government identified a set of schools that it wanted to give PASE to, high schools, but it didn't have budget for all of them, so it randomized. 64 randomly received PASE and 64 randomly didn't. So this gives us exogenous variation in the guaranteed admission incentives. Yes?
So I guess that like students didn't have to enroll in this, right? Like it was just given to them. So like if you are in the top 15%, you receive a letter or something telling you, congrats, you're a top student, you just got into, like you just need to apply to college and you will be guaranteed if this is how it works.
Yeah, so schools are PASE school or not. Schools become PASE schools. In this experiment, the announcement was also made after the deadline for school enrollment, which means that there's no strategic enrollment. And then the way it works, you have to take the entrance exam, but the score doesn't matter. You have to have been in that school for the last 2 years of high school, because PASE enters in the 11th grade. So take the entrance exam, be in the school, go to the classes, to some orientation classes, and be in the top 15% in terms of grades, and you are guaranteed an admission. However, you then need to apply. Yes. If you don't apply, you don't get it.
No, so like suppose I'm a student there, I do all the orientation classes, whatever, I'm in the top 15%, right? Is there a possibility that I check all the boxes, but then I don't know that if I apply to Chilean Harvard, I will get in?
First of all, you don't get in if you apply to Chilean Harvard because there's a whole allocation mechanism. But so basically, when students, up to the end of high school, students don't know if they're in the top 15%. Just before the window for application opens, they are told, you have a guaranteed admission. Okay. So they reach out to them. And they tell them, you have a guaranteed admission. If you apply, there's then an allocation mechanism. I'm not going to get into that now. Yes. So but it's important what you're saying, because more broadly, how do students understand? So we actually, we gave surveys to many students, 7,000 students. And in the survey, we also, at the end, we also tested their understanding of this more logistical thing. And in that, they were quite good. In other things, they're just not. It's true. So first, I'm going to go briefly over this, these findings, because I want to focus more on how you use the belief data. First, we do an evaluation using this experiment. And we find that there are college enrollment effects. So first year enrollment goes up by 3 percentage points, which is equal to 35% compared to the control group. Fifth year enrollment goes up by 1.5 percentage points. So this is a 1 if you're enrolled 5 years after high school, 0 in all other cases, yeah? No missings. That goes up by 1.5 percentage points, and that's only 30% of the control group. So that means students who enter college from treated schools dropped out at a higher rate than those who enter college from control schools. Otherwise, these two would be the same. What do we find? We are interested in this study about the pre-college stuff, the incentive effects. And what do we find there? Well, we find a reduction in grade 12 test scores of 10% of a standard deviation, quite substantial. And also a reduction in self-reported study effort. We did, we elicited information about their study. There's a bunch of questions about how many hours they study, how many days before an exam, before an exam they start studying? Do they take notes in class? Do they prepare for the entrance exam? We have a battery of questions, and we find that it goes down by 9% of a standard deviation. This especially, we see that they do less schoolwork, both in and outside of school, and they prepare less for the entrance exam. And by the way, we could do this because we were able to link our administrative data to survey data. Highly recommend. If you can get to do that, that's the best. What are the channels behind what we find? So the paper has a whole reduced form section where you, yes.
Manage the admin data.
Yeah. So the way you do it is you need to build relationships over time. So you start working with them, and then you just keep working with them. I wrote a bunch of policy reports for them. It's work that you do because obviously there's a purpose to that, but also you create a relationship that then they're more willing to sign this kind of data agreements. So that's part of the job, by the way. So it's a relevant question. If you want to collect this kind of data, and there's people here like Orazio that knows a lot more than me about this. He's done amazing work all over the world, convincing all sorts of governments. So he has more feedback, I'm sure. Okay, so we want to understand what are the mechanisms, potential mechanisms behind these impacts. Is it that they go to different types of colleges? So we looked at the major, the geographic location, the selectivity of the places they went to, and we don't find big differences between those who enter college from the treatment group and those who enter college from the control group in these characteristics. So we don't think that it's in a sense a worse college match that then leads to higher dropout. We don't think that's the case. Is it that those who enter college from treated schools are worse in terms of ability? After all, the policy did expand access, but actually in terms of measured ability, we don't see differences, and that's because there's just higher, there's more people from the top of the distribution who now apply to college. So in the end, it doesn't really lower measured ability based on grade 10 test scores. Is it worse college preparedness? Because we've seen that pre-college effort went down. So is it the case that maybe they're less prepared for college? And here what we do in this first part of the paper, we just show these correlations. So these are predictive regressions, and we control for all the baseline characteristics we have. And we see that it turns out that GPA in 12th grade is highly predictive of your persistence. So this is in the sample of those who go to college. The outcome variable is if you persist in college 5 years later. This is highly predictive. The entrance exam score is also predictive, but insignificant. It turns out that study effort, this is from our survey. So that's the value of linking survey and admin data. Study effort and baseline test scores, they both independently predict if you persist, and also hours of study per week, which is what we use in the structural model to measure effort, also predicts persistence. Of course, it could be that those who exert more effort are also more likely to persist in college for other reasons. So this is not causal, but this at least is suggestive that it could be because the policy lowered these measures of pre-college effort, maybe now these people are less prepared. So that we don't rule out, which means we're gonna put it in the model. That's what it means, we're gonna put it in the model. Also, obviously, we cannot rule out worse unmeasured ability of college entrance. That you can never rule out because I don't see it. But we're going to put it in the model as well. So we will have an observed heterogeneity that is going to affect whether you go to college or not. And so we're going to get the selection like in a control function kind of approach. And it also, an observed ability also affects how much effort you exert. So through the structure of the model, we'll be able to get the causal returns to effort. What are the channels behind negative pre-college effort and achievement effects? What are potential channels? Here, what we did was really a tour de force, because we went to these schools, and not only we interviewed all the students who were there, we went several times, made sure everybody who was in school was interviewed, actually did a survey, it was an hour long, 55 minutes. But also we interviewed the teachers and the principals, the school principals. Because this type of policy, you can imagine that a teacher now knows that their grading matters for whether the student goes to college or not. And they might decide that maybe this student has the right non-cognitive skills to do well in college. Let me bump up their grades at the cost of this other person. If grades change in that way, they're not reflective of your true academic achievement anymore. It can be a disincentive for students to then put in effort, right? So that's why we measure grading both by, we checked how grades trace standardized test scores, which we also measured, and we see that doesn't change across treatment group. We also asked questions about what grading techniques do you use, didn't change. Teacher effort, focus of instruction, which we built a measure of who the teacher teaches to. Support classes, maybe now the principal doesn't give support classes anymore for entrance exam preparation, for example, and then that then has an effect. All those things we measured and we couldn't find anything. So we rule out factors at the school level. Easy, lower perceived returns to college. So it could be this, we didn't put it in the pre-analysis plan, but when we saw these negative results, we're like, could it be that in the orientation classes, they somehow learned something about the return to college, they realize they're not as high as they thought. So now they don't care anymore about college, they stop studying, and so we elicited returns to college, expected returns to college. We actually both the expectation and the variance we elicited, and we didn't say any change on the expectation or on the variance, so even the uncertainty didn't change. How about a response to perceived incentives? Could it be that students believe it's optimal for them to reduce their effort because the return to effort in securing an admission went down? Could it be that that's the case? So if you think about it, for whom do the returns to effort go down in securing an admission? Well, if you are this type of person, if you are someone who, without the policy, you're not so far from regular admission cutoffs. So you know if you work hard, you're gonna make it because you're not so far. Reality is most of these students are way far below the regular admission. So they should not be studying for the entrance exam to start with. Turns out a lot of people do, even in the control group. So if you think that you're kind of good, kind of close to regular admission cutoffs, but if you are also top of your school, very far above the top 15 cutoff, that's the kind of person for whom we would expect the policy reduce the incentive to exert effort. If instead you're someone for whom without the policy you have no chances of making it, but then you're kind of close to the top 15% cutoff, so that if you put in effort now you might make it, that's the kind of person for whom the policy increase the returns to effort. And it turns out that in reality, and that's something that then we test with the model, most people, for the average person, that's a scenario. A previously out of reach admission is now within reach and you should increase the returns to effort. But let me show you what the beliefs look like about all of these things. So we collected beliefs about the entrance exam score. And it turns out that they think like they are like the average entrance exam taker. So they think they are minus 0.3 standard deviations. So they're around average. In reality, they're way below. So the expected minus the actual entrance exam score among those who took the exam is 60% of a standard deviation. So they expect a score that's 60% of a standard deviation higher than the one they actually get. So they think they're near regular admission cutoffs, but in reality, they're not. GPA, they know their own GPA quite well, but the expected top 15% cutoff, GPA is measured on a scale between 1 and 7. So they have a bias around the expected top 15% cutoff. So the actual minus the believed cutoff is 0.4 GPA points. So that's not much. So they think that the top 15% cutoff is a little bit below what it actually is. Not by much, by half a point on the GPA scale. But it turns out that there is so much grade compression in these schools that there's a huge mass of students in that half a point. So a small bias in absolute terms about the location of the cutoff translates into a huge bias in relative terms. As a result, 43% of them believe that they are in the top 15% of their school. And it turns out that if you look at the effort reductions, you find that they're concentrated among those who believe they're well above the passing admission cutoff, not who are, who believe they are. So this is telling us, much like in the previous paper, it seems this evidence is consistent with the idea that these people are responding to perceived incentives, not action incentives. So again, whatever you see as a check mark is stuff that we're going to put in the model. Last bit, okay, I think I don't need to study anymore to obtain an admission. However, maybe I need to study anyway because that's going to help me once I go to college. And it turns out that they think that pre-college effort does not matter for college success. So that's the last bit of the puzzle. And the reason we think this is that we've asked students, what is your, if you were to go to a selective college, which is the type of colleges they get admission to through the policy, what is your probability of, how likely do you think you are to graduate? No, how was it? Are you going to graduate? Definitely not, probably not, equally likely, probably yes, definitely yes. So we elicited these beliefs on this scale rather than using an actual numerical value. We attempted, I'll give you the behind the scenes. We've attempted that using Orazio's ruler. He had this ruler that he used in Colombia, right? But so he did interviews in Colombia to students with a ruler. Going from 0 to 100. And then there was an interviewer who, correct me if I'm wrong, who was training the student on using the ruler. So it was one-on-one interviews. And they would start with an example with rain. What's the likelihood that it's going to rain? And they play with the student until they're sure the student understood the question. Then they ask the actual questions. Now, we did not have that. We did not have that because we did not have one-on-one interviews. We had a survey. So we piloted the ruler and in focus groups in a self-administered survey, and the students just didn't get it. You just need to have that one-on-one for that to work. We piloted these questions and these questions worked. Obviously, you can see the trade-off, right? One is cheaper to get, and we could get it among many students, but obviously we don't have numerical values here. Yes.
They might think, well, the university's going to let me in. They're not just going to let me in and let me suffer. Like, they're going to help me along the way. And so it may be less that, oh, the effort, you know, there's less returns to my effort in terms of the likelihood that I graduate them. Well, actually, you know, they're not just going to pull in all these extra students and do nothing about it, right? There's going to be like additional support potentially, that sort of thing. Yeah,
so to answer that question, let's see what happens between treated and control, because those in the control group, they did not have access to this process. So if they went to university, they would have had no expectation of any extra support. And if you look at this is just a distribution, there's not a big difference between the two. So many people think definitely, yes, more than half of people, both in the treatment and in the control group. So even in the control group, there's this belief that they're going to do well. So I'm unsure about that. I don't think they expected that, because even in the control group, and here it looks like, although you never know, but it looks like people who said probably yes in the control group were more likely to say equally likely, probably not, and definitely not in the treatment group. Of course, like it's always the case in any RCT, you never know the individual level treatment effect in an experiment. So these are just averages. But this is consistent with less than 4% of the sample changing their belief. And so their belief about the likelihood of graduating. And this question was asked after the effort reductions. So to us, this is an indication that they reduced their effort, they know they did, but they didn't really change their likelihood of that much, their likelihood of persistence. We actually then allocated, we actually then did more. So this is just the raw data. Then we assign numbers to these bins, and then we run various regressions. And then we do different number assignments, more extreme, less extreme, to see how sensitive to that scaling the results are. And it's really not sensitive. We never find significant negative effects on or positive on the probability of graduating. And we also look at heterogeneity, and we find that even among those who most reduce their effort, no change in the likelihood of graduating from college. And to us, that's what made us think, well, looks like last bit of the puzzle, oops, last bit of the puzzle, perception that pre-college effort does not matter for college success. And so we're going to put this in the model. In particular, in the model, we will have an initial condition that is your subjective likelihood of graduating, which we elicited from the survey. We assume that's fixed, does not depend on anything. So that's what we got from the 15 minutes, okay. So that's what we got from the reduced form. I want to now show you how we put that into the model. And as I said, I want to give you some practical tips. So the objective of the model is, 1, replicate the experimental findings. 2, go beyond the experimental findings. How? Well, try to quantify the contribution of the mechanisms that we've identified as the likely mechanisms behind what we saw, and then evaluate counterfactual policy designs. And obviously evaluate the role of belief errors. What are the mechanisms we put into the model? Well, there's going to be a pre-college effort that affects the true admission and persistence probabilities. So you can think there's going to be some production functions and some laws of motion, objectively. So effort is going to have an objective impact on these things. Then we're going to have selection into college. It's going to be based both on observed and unobserved characteristics. So basically, we have unobserved permanent heterogeneity into the model. We do it, we have unobserved types into the model. That's because we can never rule out that the selection is worse in unobserved ways from the treatment group. Subjective beliefs. So people have subjective production functions. So they have a subjective function that links effort with admission probability and persistence chances. In particular, I already told you persistence chances, we assume they think effort does not matter at all, but we are going to also estimate the objective persistent chances as a function of effort. And then there's going to be an allocation rule. So there's going to be, underlying in the model, there's going to be objective admission likelihoods. So we're going to formalize these mechanisms in a dynamic programming framework. And before I tell you about all the steps, let me start. So the model starts with a time 0, which this is a bit less standard. There's going to be a time 0 in which beliefs are formed. So at time 0, students are going to form beliefs about the entrance exam score. It's called PSU. That's the name of the score. So B means belief. So this is going to be equal to the average expected score plus a shock around it. And we assume this shock has this variance. So this is, and we assume it's normal. So this shock, this variance is the uncertainty. Yeah, so this is the uncertainty around the average expected score. So this is a production function. This is my effort. I believe my effort translates into a certain entrance exam. These are based on characteristics. And then there's some uncertainty around that expectation, that average expectation. What are the chances of a regular admission in the model? Where it's a probability that your entrance exam score is going to be at least as large as the cutoff for a preferential admission, where again, you can think of it as an expected cutoff and then some noise around it, even though we do not elicit this one. So the reason I'm writing these equations up is not because I wanted to write equations up just for fun, but it's to point out one thing, that we write the probability of an admission as a function of the expected entrance exam score. You see that these gammas gamma 0 and gamma 1, which is what we will be able to estimate and identify, they absorb these variance terms in them, right? They absorb the variance terms. We did not elicit uncertainty. All we elicited in the survey were the means, yeah? However, when you then put your, incorporate your subjective beliefs into the data, into the model, you need to be very careful about what is the interpretation of what I've elicited. I'm telling you, the interpretation is I elicited the average. How does that truly enters into the model? Like this, I can put the probability as a function of the average, but notice that's a micro foundation. These parameters in reality have the belief uncertainty in there. I'm not going to be able to identify it, the belief uncertainty. I'm not going to be able to do it. However, you got to be precise about the mapping between what you actually estimated in the model, in the data, and how you, what you collected in the data and how you put it into the model. There's also a subjective probability of a preferential admission that depends on your GPA. So there's a GPA, a perceived GPA production function. The chances of a preferential admission are like this. The difference is that in this case, we also elicited the perceived cutoff. So this is data, this is data. So we can identify this pi parameter. What is pi? Well, it incorporates, again, the uncertainties. And I cannot separately identify the uncertainty around my own GPA from my uncertainty around the cutoff. I cannot separate them. But I need to be precise about what I'm estimating and why I don't care about it. Notice, for those of you interested about this, this is really a game. It's a tournament. It's a tournament because it's top 15%. And how do you combine beliefs with tournaments? Actually, one approach from, this is from quite standard in behavioral game theory, is that you can actually elicit beliefs about what others are doing, which in our case, it's all included in what I think the cutoff is. That's all I need to know. And assume people best respond to that. See, your probability depends only on that. And do not impose equilibrium beliefs. They don't need to be consistent with an equilibrium concept. That's what we do here. Of course, when you simulate rational expectations, it's a whole different ballgame. In that case, you do have a tournament. You need to solve for the fixed point and for the equilibrium. But in estimation, easy. I don't need to solve any equilibrium here. I just best respond to that. So another tip for you, go read the experimental game theory literature. If you're interested in this kind of thing, tournaments and beliefs in tournaments, it simplifies things a lot to elicit that. So again, I wanted to go through how we estimate these production functions. So the entrance exam score and the GPA, I need them to estimate the perceived likelihood of an admission, as I showed you earlier. How do I estimate these functions? So I'm interested in these beta parameters, which are the perceived production function parameters. So from the survey data, we directly measured the return to effort. Beta 1b, it comes from the data. How do we estimate it? With hypothetical questions. So we asked students, the question is, I'm going to tell you the question because I didn't put it on the slides. How many hours of study per week do you think you need to do to obtain a score of at least 350 on the entrance exam? How many hours per week do you think you need to study to obtain a score of at least 450? How many hours of at least 600? And then we did the same with the GPA. Here we only got 2 points. And then you can get the returns like this. So it's a ratio between, these are the values, for example, 600 minus 450 divided by the answer you gave for 600 and the answer you gave for 450. That's how we measure them. Notice that we measure them the other way around. So we didn't say, if you study this many hours per week, what score do you think you get? The reason, again, practical advice, it's all context dependent. If you collect data, you need to know the context. Talk to teachers, talk to people who know the students or whoever your subjects were. In our case, we started with the standard, what score do you think you'll get if you study X hours per week? And didn't work. Students were entirely confused. And a teacher told me, Michela, I think if you ask it the other way around, they're going to get it. And it worked like a charm. So obviously, you need to pilot everything, but make sure you know the context. So here is a distribution of raw answers. It kind of goes in the direction you expect. So for 600, they think they need to study more than for 450, than for 350. And we have it for about 5,500 students. It was a large-scale data collection in the entire country, and was still pen and paper. Okay, so this we've got it. Great, that we get directly from the data. Effort we are gonna use, because the question about the returns was hours of study per week, we need hours of study per week. So here we have a survey question. On average, how many hours of study a week did you study or do homework outside of class time during the first semester of this school year? We asked about the first semester because we went in the field in the second semester, so we knew it was done. And here, because it's a question about retrospective hours of study, we assume they don't remember perfectly. So we allow for classical measurement error, which is independent of everything else in the model. And finally, as I told you, we assume that we measure the expectation of Y. So this bit over here. And these were the questions. So we assume we measure the expectations. So here's now how we can identify all the other parameters. So we do not see effort, but we see observed effort. So let's write effort as a function of observed effort and plug it in here. This is what you get. So Y bar, this we get from the data, is equal to beta 0 plus beta 1 observed effort plus beta 2x plus something that is orthogonal to everything else, because we assume the measurement error is orthogonal. So that means that what we can do is bring this to the left, and that's data. So that is your expected test score, which we elicited, net of your expected contribution of your effort, which we measured. That's going to be equal to this. So OLS estimation of this is going to give us beta 0 and beta 2. We do this outside of the model. Again, so this, we had the data that allowed us to do that. And I'm just going to flash the really good model fit. This is the model fit to the expected outcomes. This is the mass. So we fit the data quite well, but I don't have time to go more about this. Model periods. So as I said, it's a dynamic model. Students have baseline characteristics and are an observed type. They choose effort at time 1. Time 2, they choose whether to take the entrance exam. Time 3, admissions occur according to actual admission chances. Time 4, they choose whether to enroll. And I'm just going to point out that their enrollment utility, it's an expected utility because it's the expectation between enrolling and dropping out and enrolling and persisting. And we're going to use the perceived probability of graduation, which we got from the data. It's an initial condition. We assume it doesn't depend on effort at all. And then at time 5, actual persistence realizes. Persistence depends both on unobserved characteristics and on how much effort you put in at time 1. This is the value function, the Bellman equation. And all I want to point out is that we have a subjective value function with objective laws of motion. So we have both subjective expectation and objective processes. We match the data really well. I think I'm just going to, because I need to wrap up, I think I'm just going to point out first, one thing you can get from the data is what is the true impact of effort on persistent probability. If you do not control for the type, 1 hour of effort increases your persistent by 1.3 percentage points, very similar to what we saw in the data. This is from the model. If you control for unobservables, goes down to 1. So this is telling us 77% of the correlational returns to effort are actually causal. But the more interesting stuff is on rational expectations. I think what I'm going to show is probably just this slide, just to show you what you're able to do once you're estimated the whole model. So these are the 3 main effects on admissions enrollments in first year and enrollment in the 5th year. In the baseline scenario, it's the blue bars. This basically replicates what we see in the data, the treatment effects from the data. And then we do two different counterfactuals. One is one in which, together with the policy, we give students correct beliefs about everything. It turns out students are very optimistic about the returns to effort, very optimistic about the likelihood of persisting in college. If you give them correct beliefs, it turns out the policy would have much lower impacts on admissions, enrollments, and that comes from the fact that once students realize the returns to effort are much lower than they thought, they lower their effort, and they don't want to enroll as much because they realize graduation likelihood is much lower than they thought. We do another counterfactual where we give students the true returns to effort in persistence. So we leave them biased about the level of the persistent likelihood, but we tell them actually every extra hour of study increases your likelihood of admission by one percentage point. And here we find that this policy does not do much to the treatment effect on admissions and enrollment. It increases them a little bit, but it completely eliminates the reduction in pre-college effort. So it eliminates, so I really wanted actually to, can I take 3 minutes? It's just because this is just a practical advice I want to give you. I think this is important rather than the results of the paper. I think this is more important for you. We were asked by the referees, why don't you simulate the effects of PASE under alternative cutoffs? So PASE is top 15% cutoff. Pay attention, these 3 minutes, I promise, then we're done, but this is important. Okay, do alternative cutoffs. And we're like, okay, but we know students have belief biases. We know they don't know where the top 15% cutoff is because we've elicited it. But what have we elicited? We've elicited the beliefs that they have in the current environment. It's a little bit like the paper in Pakistan. Given the current environment under this top 15% policy, under the what is a top 15% cutoff? If the policy was not top 15%, but it was top 20% or top 10% or top 5%, well, the distribution of GPA would be different, and probably also the beliefs that people have would be different. Have I measured those beliefs? I haven't. I didn't ask them, what do you think the cutoff would be? Also, I don't think they would be able to answer such a complicated question. So this is a question about counterfactual beliefs. So whenever you have subjective beliefs in your data, you know that people don't respect rational expectations, you measure subjective beliefs, and you want to do a counterfactual that changes something about the environment, you need to either have already collected the counterfactual beliefs, or you need to come up with a model for how those counterfactual beliefs are built. We didn't have the beliefs, so we came up with a model. Which model? Well, we assume that their belief errors are constant in the counterfactuals. What does it mean, constant in the counterfactuals? And that's the question I want to ask you. So there's 2 ways I can think of measuring a belief error, this belief error that needs to be constant in the counterfactual. So I am assuming that they have a belief error that is constant over what? So their believed 15% cutoff versus what? The actual cutoff that I see realized in the data and that my model replicates at baseline? Should I do that? Or should I take the difference between the believed cutoff and the rational expectation cutoff? Obviously, these 2 are not the same because I know they're not playing rational expectations. They don't have rational expectations. Which one do you think I need? So I'm going to build a difference between your perceived cutoff, this, and either that or that. And then I'm going to assume, remember the purpose, I'm going to assume that difference, that delta is constant in the counterfactuals. Which one of the 2 should I use? Try to think about it. Something that allows me to then do the simulations in the counterfactuals. So the idea is I want to get this delta. I measure the delta. Now I need to be able to simulate a counterfactual scenario with a top 20% cutoff where I can add this delta on top. But I need to be able to simulate this counterfactual scenario to add this delta to then get the beliefs. Yes.
The rational expectations, because the realized cutoff is going to vary cohort by cohort, right? So
it is, yes.
Specific cohort, then yeah, you want to know like the distribution, like the extent of the distribution rather than the actual outcome.
So I'm not sure what you mean by cohort, but it is a rational expectation cutoff. And the reason is that otherwise I would not know where to add this delta to in the counterfactuals. So I must be able to simulate the benchmark also in the counterfactual policy. How can I, this is circular, how can I simulate this benchmark, which depends on the belief biases that I have in this scenario? How can I simulate it in the counterfactual? It's circular. That's exactly what I cannot. It's exactly what I'm trying to do. So what is the algorithm? Assume students will exhibit the same belief bias relative to the rational expectation cutoff as they do under the top 15% rule. Then in the baseline, I compute this bias. I see it in the baseline because I elicited the top 50, the perceived cutoff, and I see the rational expectation cutoff. I've simulated the rational expectation cutoff. I get the delta. Now you do a top 20% rule with rational expectations. I can't solve it. I can solve top 20% with rational expectations. And now I get the top 15% cutoff under the rational, top 20% under the rational expectations. And to that, I add the delta. And that's my new belief. It's a rational expectation cutoff plus a constant delta. And now I solve the model with this new belief. So this really what I want to convey is be very, very careful about the counterfactuals when you have subjective beliefs, because you do need to build the counterfactual beliefs. And you need to think very carefully about how you build that. I'm going to finish on that. These are just the results from the different cutoffs. I'm going to finish on that. I'm sorry I took 7 minutes of your time extra. I hope it was helpful. Thanks.